Now this is another famous vector integral theorem after the Green's and the Stokes theorem. This deals with closed surface integrations. So a Gauss divergence theorem provides a connection between closed surface integral and a volume integral. Suppose we have a field F, F1i plus F2j plus F3k, and suppose S is a closed surface then the closed surface integration of F dot n cap ds is identically equal to the volume integral of divergence of F. Specifically, if F is a solenoidal field, divergence F would be 0. Therefore, closed surface integral F dot n cap ds would be 0. This is one of the simpler situations. Suppose F were a field which looks like Axi plus Byj plus Czk, then divergence of F would be A plus B plus C, which is constant. Therefore, closed surface integral F dot n cap ds would be triple integral or volume integral A plus B plus C times dV. This is nothing but A plus B plus C times the volume of the solid. Now, if the divergence were neither 0 nor a constant, then serious triple integration would be required. So, let us look at some illustrations and see what type of questions can be expected for this type of examinations. Question number 1. What is the output of closed surface integration e power x dy dz minus y e power x dz dx plus 3z dx dy, where S is the surface of the cylinder, x square plus y square is equal to c squared, and 0 less than or equal to z less than or equal to h. So, from the given integral, we can extract the field, and it will be e power xi minus y e power xj plus 3zk. Now, instead of evaluating the closed surface integral, to produce the answer we use the Gauss theorem and take the RHS of the Gauss theorem as divergence of F dV over V. Divergence of F would be dou by dou x of the first component plus dou by dou y of the second component plus dou by dou z of the third component. So, this would make it e power x minus e power x plus 3 dV. This will reduce to 3 times volume integral dV. So this is nothing but 3 times volume of cylinder. Now what we are given is a cylinder with height h, and this will be 3 times pi r square h. This will be 3 times pi. The radius of the circle that is given to one is because this radius is c units and the height is h. So 3 pi c square h is the output of this answer, and the correct option is D. So the advantage with this problem is no serious integration, volume of the cylinder. You must only know the dimensions of the cylinder. From the given equation, we can find out that c is the radius and h is the height of the cylinder. Let's go to the next question. Question number 2. What is the output of closed surface integral yz dz dx plus zx dz dx plus xy dx dy, where S is the surface of the sphere x square plus y square plus z square is equal to 4. So from here the field can be extracted, yzi plus zxj plus xyk. Once again we convert using the divergence theorem, and we can convert it into a volume integral, divergence of f dv. So divergence of f would be dou by dou x of the first component plus dou by dou y of the second component plus dou by dou z of the third component. So you will find that you will get 0 plus 0 plus 0 dV, that is 0. So no serious integration at all. But if you will not be knowing the divergence theorem, then you will be into a lot of trouble, lots of integration, but you finally produce only a 0. So the correct option for this problem is A. Question number 3. What is the output of closed surface integral x cube dy dz plus x square y dz dx plus x square z dx dy, where S is a closed surface of the circular cylinder x squared plus y squared is equal to a squared, and the circular discs z is equal to 0 and z is equal to b. So we can extract the field F is equal to x cube I plus x square y j plus x square z k. Once again, by divergence theorem, the answer would come from volume integral divergence of f dv. This would be volume integral 3x squared plus x squared plus x squared dv. This is volume integral 5x square dv. Now the cylinder that is given to us has base on the xy plane, the radius is A units and the height of the cylinder is B units. So the equation of this circle would be x square plus y square is equal to a squared. This will be the region of double integration. So first what we do is we integrate with respect to z. So you will get 5 times double integral over r 0 to b x square dz dx dy. Because dv can be written as dx into dy into dz, we have promoted dz into the order first because the integration with respect to z is first. So this will become 5b double integral over r x square dx dy. So now this double integration should take place over the circle, so we can use polar coordinates. So we can write 5b times integral 0 to 2 pi integral 0 to a r cos theta whole squared into r dr d theta. So let's do this evaluation. So this would be 5b times integral 0 to 2 pi r cube when you integrate becomes r power 4 by 4 from 0 to b, this is 0 to b, 0 to a rather, d theta. Of course cos square theta is also there, cos square theta. So this becomes 5a power 4 b by 4 0 to 2 pi cos square theta d theta. Now we can write this 0 to 2 pi range as 4 times 0 to pi by 2. So 5a power 4 b by 4 into 4 times 0 to pi by 2 cos square theta d theta. But by this time all of us know this is a well known integral and whose value is pi by 4. So 5 pi a power 4 b by 4 is a correct option. Now this is a fairly decent question because it goes through a little bit of double integration where polar coordinates will be required. The correct option for this problem is C. Question number 4. What is the output of closed surface integral 9x dx dy plus y cos hyperbolic square x dz dx minus z sin hyperbolic square x dx dy, and S is the surface of the ellipsoid 4x square plus y squared plus 9z squared is equal to 36. So first extract the field 9xi plus y cos hyperbolic square x j minus z sin hyperbolic square z k, and S is the ellipsoid 4x squared plus y squared plus 9z squared is equal to 36. So well, this is a three-dimensional object, but first let us look at the application of the divergence theorem. So the RHS of the theorem would be volume integral divergence of f dv. So you take the divergence of this field, which would be dou by dou x of 9x plus dou by dou y of y cos hyperbolic square x plus dou by dou z minus z sin hyperbolic square x dv. So this would be volume integral 9 minus cos hyperbolic square x minus sin hyperbolic square x dv. But all of us know this is equal to 1. So this is 10 times volume of the ellipsoid. And let us look at this ellipsoid. This can be written as x square by 9, rather x square by 9, yes, plus y square by 36 plus z square by 4 is equal to 1. So if you imagine this as x square by a square plus y square by b square plus z square by c square is equal to 1, a would be 3, b would be 6 and c would be 2. Now why are those things required? That is because 10 times volume of ellipsoid would be 10 times 4/3 pi ABC. That is the reason why we require the dimensions of the ellipsoid. So now this would be 40 pi into A is 3, so it will get cancelled with this 3, B is 6 and C is 2. So this is 12 fours are 40, so 480 pi. So this is the output of this particular integral, and therefore the correct option for this problem would be C. Question number 5. What is the output of surface integral f dot n cap ds, where the field f is equal to 2x square yi minus y square j plus 4x z squared k, taken over the region in the first octant bounded by the cylinder y square plus z square is equal to 9 and the plane x is equal to 2. So the question is to evaluate f dot n cap ds. The field is given as 2x square yi minus y square j plus 4x z squared k, and the surface is y square plus z square is equal to 9, x is equal to 2 in the first octant. First, let us visualize the diagram. Now this is a cylinder with base on the yz plane. So yz, this is x axis. And because it is in the first octant, the diagram should be drawn something like this. So this curved surface corresponds to y square plus z square is equal to 9, and this height is 2 units along x direction. So if at all we have to integrate over the yz plane, the region of double integration will be the quadrant of a circle. Okay. So let's convert using divergence theorem. So the answer can be computed from the right hand side of the divergence theorem. This would be dou by dou x of 2x square y, that is 4xy, minus 2y plus 8xz dv. And we will first integrate in the x direction because those limits are clear. So double integral over r, x is equal to 0 to 2, 4xy minus 2y plus 8xz dx into dy dz. So we first integrate with respect to x. Double integral with respect to x, you will get 2x square y minus 2xy plus 4x square z. So when you apply limits, this will become 8y minus 4y plus 16z dy dz. So let us see how to handle the remaining part. So this will be double integral 4y plus 16z dy dz. So you must now refer to the diagram. The region of double integration is the quadrant of the circle 0 to quadrant of the circle on the yz plane. So we can convert to polar. Y is equal to r cos theta, z is equal to r sin theta. Of course, we know Jacobian is r, so dy dz becomes r dr d theta. Radius varies from 0 to 3, you can see that from this equation, and of course theta varies from 0 to pi by 2. So it is all now very simple. Within these limits you can perform the integration. So those last parts I will leave it to the students calculation, but I will just set up the limits 0 to 2, 0 to pi, 0 to pi by 2 rather, 0 to 3, 4y becomes 4r cos theta plus 16z would become 16r sin theta into r dr d theta. So we will have to perform integration with respect to r first, apply limits from 0 to 3, and then the remaining trigonometric functions integrate from 0 to pi by 2. You can easily find the answer will be 180 and the correct option will be C. So please try out that last part, which is not at all a difficult thing to do. So with these illustrations we come to the end of Stokes theorem and also to the end of the vector integral theorems area.